Good day, everyone. For today, we are going to learn about linear transformations. Linear transformations. Definition of a linear transformation. Let V and W be vector spaces. The function T that maps the vector space V into the vector space W is a linear transformation of V into W when the two properties below are true for all vectors U and V in V and for any scalar C. Number 1, we will have the transformation of a sum U plus V is equivalent to the sum of the transformation T of U and T of V. And then, number 2, we will have the transformation of a scalar vector CU is equivalent to C times the transformation of the vector U. Okay, let us have an example. In this example, we are asked to verify whether T is a linear transformation from R squared into R squared. Show that the function in example 1 is a linear transformation from R squared into R squared. So we will have the transformation of the vector V, whose components are V sub 1 and V sub 2, is the following. So we will have for the first component, V sub 1 minus V sub 2, and the second component being V sub 1 plus 2 times V sub 2. Now we know that in order to prove whether a function is a linear transformation, we have to make use of the following. We need two vectors U and V in V and another object which is a scalar C, such that T of a sum of vectors is equal to the sum of the transformation of the vectors. And we will have the transformation of a scalar vector equal to C times the transformation of the vector U. So let us do that. Let us have two objects which are vectors. We have V, and whose components are V sub 1, V sub 2, and U, whose components are U sub 1, U sub 2. So again, we will have the properties of vector addition and scalar multiplication. We were able to use the two statements below, that is the transformation of a sum, which is given by T of U plus V1 and U2 plus V2. So applying our transformation, we will have U1 plus V1 minus U2 plus V2. And then we also have for the second component, U1 plus V1 plus twice of U2 V2, and then collecting all the terms that has the U, you will have U1 minus U2, and then V1 minus V2 for the first component, and the second component you can also group the terms that has the U as well as those terms that commonly has the V. You have U1 plus 2 U2, and then plus V1 plus 2 V2, and we simply gather all the terms which are actually components of the vector U. So you have U1 minus U2 in the first component, and the second component being U1 plus 2 U2, and then plus you will have your V sub 1 minus V sub 2 as the first component of our V, and then we will have V1 plus 2 V2 as the second component for the transformation. Know that U1 minus U2, comma U1 plus 2 times U2 is simply the image of U, and V1 minus V2, comma V sub 1 plus 2 times V sub 2 is just the image of V, and hence we were able to prove that T of U plus V is just T of U plus T of V. And with regard to the scalar multiplication, we will have, we know that CU is given by C times U1 comma U2, which is CU1 comma CU2. So in order to according to the transformation, the first component being, first component minus second component, and then for the second component, we will have first component plus twice the second component, and then we simply factor out C, we will end up with u1 minus u2 comma u1 plus 2u2, which is actually just the image of the vector u. And hence, t of cu is just equal to c times t of u. So t is a linear transformation.